Okay, so last time we ended with, we got to digital signatures. I didn't really expect that we would get that far, but we talked about it a little bit. So digital signatures are kind of like, they have some similarities to actual signatures. I actually one time got a passport application rejected because I printed my name like this. And they sent it back to me. I had to leave for another country in like one day, and they're like, passport denied, because like I didn't write it in cursive or something, and I was so furious. But the point of a handwritten signature is to establish your identity, and you put it on documents, and it means that nobody else could have approved of the doc, or you at least had to see the document and things like that. Of course, it has many problems. So this is in the section on public key cryptography. So public key cryptography basically has two applications. One is key exchange, like Diffie-Hellman key exchange, which we've been talking about, and the other is digital signatures. So this is basically how it works. So of course you have a private key and a public key. So the private key is used for signing. So only you have your private key, and so you apply it in a special way to a document that only you could have done. And then the public key is used for verifying the signature. So, you know, the public and private key sort of lock together in such a way that everybody can have the public key and they can kind of tell that the private key has been applied, even if they don't know exactly what it is. So to draw it all as a diagram here, you could have some document X, and this goes into some kind of digital signature machine. So we'll talk about two ways to do this today. And what comes out is a signature, which we'll call S. And the ability to do this depends on having the private key. So then Alice transmits X and S together to Bob. And so Bob has to verify. So he puts X and S together into his verification machine. And the verification machine requires the public key. And what comes out is either, you know, accept or reject, depending on whether or not the signature is valid according to the verification algorithm. So you could either reject or accept. So notice here that X wasn't encrypted. So digital signatures, their purpose is not to provide privacy, but they do, you know, we've talked about this, I think, earlier in the class, so I just like to be able to know this. So the four important cryptographic services that we learned about in this class anyway are confidentiality, or privacy. So that has to do with, you know, obscuring your communications using AES or DES, for example. But then there is message integrity, which is also important. And there's message authenticity. And there is non-repudiability. So we've spent most of the course talking about AES and other ciphers. So ciphers ensure confidentiality, but not any of the other things. But digital signatures provide these three things. So digital signatures provide message integrity. So when do they provide message integrity? Let's say that Eve interferes with this transmission and changes a bit either of the signature or the message or something like that. This could also be ciphertext, by the way, and then Bob could just decrypt it when he receives it. So if there's no way to, without knowing the private key, there's no way for Eve to change this at all in a way that won't show up later during the verification stage. So if this is corrupted, then when Bob tries to verify, the verification will fail, and he will know that some change has been made. Also, it gives you authenticity. So so what does that mean? What does authenticity mean?
Only who is supposed to have access can
Yeah,
get access.
it means you're certain who sent the message. So if you know who sent the message, then you can verify the authenticity of the message. So you know that it's from the president or whatever. So digital signatures provide authenticity. Can you think of why? Something to do with this. So a private key is like a social security number. You know, only you know it. Except in reality, everybody knows your social security number, and private keys are much better than social security numbers. But your private key is you. So if you sign something using your private key, only you could have done it. And so that gives you authenticity. People say, by the way, that authenticity implies integrity, because if I send you a message and it gets modified in transit, then it's not really from me now, is it? And so if you can be sure that a message is what I wrote, then you also need integrity. There's this fourth property called non-repudiability. Anybody remember what that one means? That means that I can't deny having sent the message. So if this message sends, it says something like, when I die, Aiden gets my car. I can't later claim that I never sent the message because I digitally signed it. And so there's this assumption that only I have my private key. So you could use this for financial transactions, and that's sort of how cryptocurrency works. But lots of kinds of transactions could work that way. You could do digital voting, for example, which is becoming more and more relevant to all of our lives. This talk that people are having about like voting, like large scale voting for president by cell phone, is a terrible, terrible idea. I hope they don't do that. But with digital, you know, if every citizen were assigned a private key and could manage it, like 256 secret bits that only they knew, then we could do all kinds of stuff, including secure online voting. But it doesn't seem to work like that, you know, like what is your name, date of birth, last four of your social? That's stupid. That's never going to get us, that's just a recipe for disaster. So you could do digital voting in theory, identification management, like payment, commerce. You can sign contracts. You might have heard of these things called smart contracts. You know, signatures make those possible too. And you have X509 certificates. Have you guys ever heard of these? I know you've gotten this error on your web browser that says something like certificate not valid, right? Probably some point.
I think I've seen 509, but not X509.
So the thing with these internet certificates, and when your browser starts yelling at you like danger, cannot verify certificate or something like that. So let's say you go to Amazon and you want to use HTTPS because you don't want people to see what groceries you're ordering or to be able to read your credit card from the channel. You have to do key exchange with Amazon, and in order to do that, you need to use public key cryptography to agree on a key. But how do you know what Amazon's public key is? So you have to have Amazon's public key in order to do key exchange. But then, so you go to Amazon.com, and then in the course of these TCP packets flying back and forth, you receive a number which purports to be Amazon's public key. But how can you verify that it really is? It could be from somebody trying to trick you. And there's a You know, that's possible. So the way certificates work is there are these certificate authorities, and they write these certificates that basically say whose public key is what. And it's like a chain of promises. So there's some certificate authority that says, like, for example, you know, you should trust there's one organization that signs a certificate that says you should trust this other organization, and then they sign certificates that say you should trust these other people. And so it's like a chain of digital signatures that give you like a chain of trust back to some ultimate trust authority, which is the certificate company, like VeriSign, for example. And some public keys are baked into your browser. That's what gets the whole process off the ground, like DigiCert or VeriSign. Their public keys are probably baked in, I mean, like at compile time, like written into your web browser. So your web browser knows those. So then if you later get a certificate that's signed by DigiCert and it says that Amazon's public key is XYZ, then you can verify that signature using the baked in public key in your browser, and then you can be certain that Amazon's public key is whatever it's supposed to be. So that's called public key infrastructure. And we're not going to talk about it in detail. There's like a whole chapter of the textbook on it, but we're definitely not going to have time for it. But it's important to vaguely understand how that works. Okay. So last time we talked about using RSA for digital signatures. And it's very simple. So let's say that you, by the way, this is called the school book version because it has a bunch of problems, kind of like with RSA cipher, but you can easily fix them if you're careful. So we'll present it in the simplistic way first. So you have some document that you want to sign, and this is, so you know, RSA has these public keys. N is the product of two large primes. And then you have the public exponent, and then you have the private exponent, which is the inverse of the public exponent, mod phi of n. And then you have the whole thing that makes RSA work, which is x to the ed is congruent to x mod n for every x. So let's say that you have this document here that you want to sign. So it might be a big document. It might be bigger than, you know, n will be something like a 2048-bit number. So if your document is a couple megabytes, you might have to hash it first or reduce it somehow. And actually later we'll talk about padding. But to produce a signature, the signature is just x to the d, where d is the private key here. So this is the number which only you know. So only you know D, so only you could have produced the signature, and then Alice will transmit the message together with the signature to Bob, and then this is the signing process. And now Bob will receive this, and he will just ask himself, is it true that x is equal to, so here's a question, is it true that x is equal to s to the e mod n? So Bob can compute that because the public exponent is public. And what is this value? It's x to the de, which theoretically should be equal to x mod n. So if this is true, then Bob will, so if this is true, then Bob will accept the signature. And if this is false, then Bob will reject the signature. All right. So a couple things to observe here are, one is that, you know, the public exponent is usually small. It's like 2 to the 16 minus 1, which is 1 followed by several zeros, 15 zeros, and then a 1. There are actually more zeros here. But when you exponentiate by e, that's what happens in the verification process. So to verify, you exponentiate by E. Okay, but to sign, here's the signing process. When you sign something, you exponentiate by D. All right, and which one of these processes, so E is this short, simple number with lots of zeros, so it goes very fast in the square and multiply algorithm. But D is basically a random choice inside that group, which is approximately just as big as N. And so what D is some big long monster number with a mix of ones and zeros. It's like 2048 bits long. So this exponentiation is going to be much, much more expensive than this exponentiation. So, so which one is faster, signing or verifying?
Verifying?
Yeah, verifying is much faster. And let me share my terminal here if I can find this. Yeah, here it is. So there's this fun command that you can run. You guys see a terminal right now? You could do this on CoCalc or on your own machine. Do OpenSSL speed RSA, and then it does like a speed benchmark. It computes as for various bit lengths. So first it tries 512 bits, and then it goes all the way up to 15 360 bits. It does as many operations as it can in 10 seconds, and then it gives you this summary of the performance of your computer. So your computer can probably beat mine. It's not super great or anything. This is the number of signatures that it was able to do in 10 seconds. And notice that's much smaller than the number of verifications. The factor between these two numbers gets worse and worse the more bits you have. So like, where is it easy to compute? Like right here, it says roughly 50, right? So verification is about 50 times faster. But by the time you get down here, verification is about 200 times faster. So the sort of ratio gets worse and worse. And this is kind of amazing. You can only do 6 signatures a second with this big RSA key, considering how fast computers are and that you're just doing like quote unquote one mathematical operation to do the signature. It's kind of amazing that it's that slow. But, so you could try that on your own computer. It might be fun to see what happens. Let's come back here, and we need a new page. All right. Oh, and by the way, that is good for these certificates that we were talking about, the X509 certificates, because they're signed once, but they're verified over and over and over and over again. So it's important that the verification go faster. So RSA is good in that way. Okay, so here is a one bad thing about this. You know, we said we did the school book version of RSA. So let's just show one terrible thing that could happen. By the way, even without giving an example, there's one shortcoming of schoolbook RSA, which is that it's deterministic. So if you sign the same document twice, then you get the same signature twice, and that's not a desirable property. So in the examples we gave above, we didn't care about confidentiality, but maybe you do. You know, if you can prevent it, it's better to stop the signature from leaking information about the document that was signed, if you can avoid it, which you can, by making signatures probabilistic. Oh, Aiden, hello, you raised your hand.
Yeah, I just didn't want to interrupt you. Is it kind of like how each person ideally kind of has like their own unique signature, like their own handwriting, but like if somebody was to like forge your handwriting or like forge your signature, then they can use that to like, I don't know, sign like basically like impersonate you with your signature. Like, is that kind of how it is? Because you're verifying with the same signature multiple times?
Yeah, and so if I can learn your, let's say that I learn your private key, then I can be you. You know, I can like buy a couch on eBay or something. So if I have your private key, then anything you can sign, I can sign. And so that's like, you know that I'm about to do the forgery probably. So I'm going to show you a different kind of forgery that Schoolbook RSA is vulnerable to, that doesn't require knowledge of the private key, but it's also sort of less useful. So what is a forgery? So a forgery is any pair XS, so that if I were to verify this, then I would think it was legitimate. And if I can produce a pair like this without knowing the private key, then that's a forgery. So one way for me to, I don't know if you would really call it a forgery if I stole your private key and then, but let's do call that a forgery. So one way to forge something is if I just steal your private key. But you could also do this other ways. Like for example, if you were able to factor, well, if you're able to factor n, then you could recover d, and then you could. This is also just knowing the private key. But you shouldn't be able to produce any pair x and s, so that if you put it into the verifier, it accepts it. And so the vulnerability that Schoolbook RSA has is actually not that bad, because you can produce a forgery. So you can produce a pair like this that the verifier accepts. But when you do it, X can't be anything that you choose. It has to be sort of pseudo-random garbage. But it's still a problem because, you know, like when you do cryptography, it's really servers doing it, and so they have like insect brains. So maybe you can make something go wrong if you can send it something that it verifies, or something like that. So it's an undesirable property for any signature scheme to be able to produce some pair that verifies if it wasn't produced, you know, in a proper way. So here's by the way, when X is possibly garbage, they just call that an existential forgery. It just means that one exists. And so a worse case than an existential forgery would be like a targeted forgery where you were able to sign a document that actually was meaningful. But if a forged pair like this just exists, they call it an existential forgery. Okay. So here is Bob over here. And Bob picks his, he has a private key. You know, they've already, let's say, I guess Bob is deciding on his RSA parameters here. So he has a private key, which is D, and he has a public key, which is N and E. And he publishes these to the web. So everybody knows N and E. And then there's some malefactor, some bad person in the middle here. The book calls them Oscar, but I kind of hate that name. I kind of like Mallory better. So here's Mallory in the middle. So the way this attack works is Mallory can choose any signature she wants. So she chooses, it doesn't matter what S is. She chooses some S and Z to the end. So maybe it's just like 2048 ones or something. And then the message is determined by the signature. So she has to pick the message just to be S to the E mod N. And so now she's produced this pair X and S. Now, if Alice puts this through the verifier, so what does it mean to verify? She asks, is it true that X is equal to S to the E mod N? And what is the answer to that question going to be? Yes, just because that's what X is defined to be. So, you know, this is sort of like encrypting this S that she chose, and so she's not going to be able to make S anything meaningful, like, you know, a contract or anything like that. X is just going to be gibberish, but this will still verify, and so it's an existential forgery. So it's bad that can happen. So there are a couple of ways to avoid this. Like the easiest way to stop it is instead of signing X, just sign the hash of X instead. But a better way is to use a padding scheme. And the padding scheme that we used for our RSA cipher is not the same as the padding scheme that you should use for signatures. So that would be like, this would be the kind of cryptographic mistake that you could realistically make in the real world. Like, you know that you're supposed to pad, but you use the cipher padding instead of the signature padding, and when you write your code or whatever. So PSS, what does this stand for? Probabilistic signature standard. And I will admit to just straight up screenshotting the diagram of this from the book. So where is it? Right here. Okay. So M is the message, and this little h here is a hash function. So even in PSS, you're still hashing the message. This padding here is a special number or pattern that is just specified in the PSS protocol. And anybody know what salt is? Have you ever encountered salt before?
No.
It's a really terrible movie with Angelina Jolie. And cryptography, salt is a random number, and so this is just a random value, and it's what gives it's what puts the probabilistic in PSS. So for every different message that you sign, you'll change the salt, and so that makes different signatures happen for different messages. So you produce this, and then it's hashed again, and then it comes down here to produce H, and then this BC is just a special pattern that is part of the protocol for PSS, which everybody knows. And then there's this step here. It goes through this function called MGF. I think that's message generating function, but it's basically just another hash function. And then there is this part. The point of this salt is the same as that salt. And the point of this is so that the recipient can find out what the salt was. And here there is some more padding, and the padding is also determined by the PSS protocol. So when somebody receives this message, what are they going to know? They're going to know BC, they're going to know both of these padding values, and they're going to have access to this function and this function H. And so they're gonna, oh, I should say, here you have EM, this final thing, right? EM is like, it's an element of ZN, and EM is what's actually gonna get signed. So when you sign your document, you're actually gonna be raising EM to the dth power. So then after you sign EM, you raise EM to the dth power, and then you transmit it, and then the verifier raises that to the eth power, and they get EM back. So let's say you're in the position of the verifier, and you have this EM here, and you also have a copy of the message, and you want to know if the signature is correct. So it is correct if EM decrypted correctly. So in other words, if you really have EM. So how do you know if you have EM or not? Well, EM has a lot of structure. So you can, this step right here is a lot like a Feistel cipher. And you know that Feistel ciphers sort of go backwards if you push them up instead of down. So just push this part up. So that will XOR this H with this thing. And what that will give you back is padding and salt. So now you've recovered the padding and the salt. Well, okay, you don't care about the padding, you knew that before. But so you've recovered the salt. So now that you have the salt, you can take the message yourself and do this whole process. So you take the message and hash it, and then add the salt, and then do all this stuff, and you can ask yourself, did I get EM? And if the answer is yes, then the signature is valid. And if the answer is no, then the signature is invalid. Anyway, so this has just sort of added a lot of structure to the thing that gets signed. So you can, it's not just any message that will, you know, and when we did the attack, the message was gibberish. It had no structure. But now we won't accept messages like that. We only accept messages that have this nice that satisfy this structure, and so you can't do the trick that we were talking about a second ago. Okay. All right. So now we're going to go on to the El Gamal signature scheme. Oh wait, I wrote in case you care, I did the RSA. Did the RSA? I think it's here. Is it there? I did RSA and Sage. In case you I should probably be making you guys do this. But here's the RSA signature algorithm. You know, you have some number, some prime, another prime. N is their product. You need Euler phi because you need to find D. So you pick some E, and it has to be true that E has an inverse mod phi n. Then D is that inverse. Now to sign a message, you raise x to the power d mod n. So in this case, you get 68. And then to verify, you just raise s to the eth power and ask if it's equal to x, which is true. So that worked. That's the school book version, of course. Right. So the next topic is El Gamal signatures. So this is the same Tahir El Gamal that designed the cipher that we've already talked about. So why are we talking about this at all? The basic reason is we've talked about RSA, so that is a signature scheme whose security depends on the integer factorization problem. And now we're going to look at an example of a signature scheme whose security depends on the discrete logarithm problem. And so that's El Gamal. And El Gamal is also very similar to DSA, which is the digital signature standard that's very often used. So that's one good reason to understand El Gamal. It's just like a stepping stone for understanding DSS. I think we're not actually going to go through DSS in detail. One reason is because it's so similar to El Gamal. So this is getting, you know, close. People do use RSA a lot in practice too, but they might use DSS more. I'm not sure. So this is like a baby version of that. Okay, so here are the public parameters. You know that if you just, it's hard to connect this with El Gamal cipher, but if the basic outline of the El Gamal cipher was you had the setup for Diffie-Hellman key exchange, and then you agreed on a shared secret. And then you use the shared secret as a multiplicative mask to encrypt the message. So it's hard to see a similarity between what we're about to do and that, but the start where you set up basically you set up the parameters for Diffie-Hellman key exchange, that part is the same. So you need a large prime P. And this has to be just as big as in Diffie-Hellman key exchange. So like at least 1024 bits and 2048 would be better. And you need a generator. So choose alpha, which is a generator of the multiplicative group mod P. Okay, and then you choose your private key. So D is going to be the private key, and it should be selected uniformly at random in ZP. So the book says don't pick one, or don't let it be plus or minus one. But if if P is 2048 bits, what are the chances that you're going to get plus or minus 1? It's like nothing. But anyway, so if if you do this and D turns out to be plus or minus 1, then throw it back and pick another one. And so that's the private key. Maybe I should write that here. So this is the private key. And the public key is going to be alpha to the D, mod P. Okay. And, so now beta contains a lot of the same information as it's like it's built based on the private key, so it has the private key built into it, but nobody can learn the private key from beta because of the discrete logarithm problem. So the thing that stops people from going from beta and recovering the private key is the discrete logarithm problem. So this is the public key. Right. So how do you sign a message? So the signature is 2 numbers in this case. It's kind of interesting because in the El Gamal cipher, the message was doubled in length, and here this signature is doubled in length for sort of arguably similar reasons. So here's X, which is a message to be signed. So it's something in ZP, the message. Okay, so in order to make a signature, you need an ephemeral key. This one you just make up. So KE is selected uniformly at random in ZP. And of course, it should not, not 0, 1, or minus 1. But if P is big, then the chances that it's one of those things is like 0. This has to have one special property, which it needs to be invertible modulo P minus 1. So we require that the GCD of the ephemeral key and P minus 1 is 1. And that's just so that the inverse exists. So KE minus 1 mod P minus 1 exists. All right. Let me add a new page. Okay. All right. So here's how you produce the signature. So the signature of X, which is made with the private key, which remember is just D, this is equal to a pair RS. So it's a pair of numbers. And this is how you make each one. So R is equal to alpha to the KE mod P. I think of this as being like roughly similar to the shared, well, I don't know. I keep trying to find the connection between this and the cipher. It's a completely different algorithm, but I'm just trying to like compress this information. So that's R, and then this other value S is equal to X minus D times R times KE inverse mod P minus 1. So this is a little bit different. So it's P minus 1. That's because this stuff is going to be happening in the exponent, and I'll say more about that in a second. So there are a couple before we show. So the signature part is done. So that's your signature. That's how you compute it. The only place that the private key gets used is right there, where D gets multiplied in. So as a warm-up for understanding how the verification works, let's just look at a couple of values here. Like one important one is R to the S mod P. So what is that? That's alpha to the KE. So that is, that's what R is. And then we're raising that to the S, which is, let's just write it like this for the time being. So this becomes alpha to the Ke times Ke inverse times x minus dr period, okay, mod p. Okay, all right. So it looks like these things are going to cancel, and they do cancel, but let's do a sanity check here. So why should they cancel? It's because alpha to the p minus 1 is congruent to 1 mod p because of Fermat's little theorem. So you have the order of alpha divides p minus 1. So if something is if you raise alpha to any power, all that matters is alpha to that power mod p minus 1, because if you write down p minus 1 alphas, it's all going to start over again anyway, because this is saying that products of alpha cycle around to be 1 again after p minus 1 tries. So if you have some exponent that's congruent to some other exponent mod p minus 1, then it's not going to affect alpha to that power. And that's why this was p minus 1 instead of p. Okay, so that's just to say that this stuff cancels out. And now you have, this is equal to alpha to the x minus dr. Okay, all right. So now you also have, you have beta lying around here. So remember that beta is equal to alpha to the d. So here you have a d occurring negatively, and here you have a d occurring positively. So maybe you can cancel them out. And you can cancel them out like this. First you raise beta to the r power, and then you get alpha to the dr. And now look what happens if you multiply these things. If you do beta to the r times r to the s, so we know what r to the s is. That's what we just figured out here. So r to the s is congruent to that mod p. So now you get alpha to the x minus dr times alpha to the dr, and these exponents add, and you just get alpha to the x mod p. Okay. So as we were doing that, this is actually the verification. So the signature is valid if this equation is true. So that's how you check validity. Why does it check validity? It's because beta has d baked in. And so the person who formed the signature had to know d in order for this cancellation to occur. So if it does occur, which you can check using this equation, then that means that the document really was signed using the private key. And so the signature should then be valid. So this is the validity check. Okay, so to check the validity, you verify that b to the r times r to the s is congruent to alpha to the x mod p. Okay, so let's do an example with some small numbers. So let's say that p is equal to 23. And I'll just randomly pick the ephemeral key to be equal to 3 in this example. And then if you figure out what the inverse of Ke mod 22 is, it turns out to be 15. So remember, this is the inverse mod 22, not 23. All right, and so we need a document to sign. Oh, I have to pick some more parameters. So alpha is supposed to be a generator of Z23 star. If you try a couple of values, you can quickly find that 5 works. And once you decide that alpha is 5, then you can figure out beta, because beta is alpha to the d. And oh, I haven't picked d yet. Let's just say d is equal to 10. All right, so these things that are, I was supposed to pick this at random anyway. So I picked this at random and it just turns out to be equal to 10. I was supposed to pick this at random and I did, and it turned out to be equal to 3, and then I compute its inverse. This stuff is, P and alpha and beta are all public, and D is private. And it turns out that beta is equal to 9. And so if you want to do it yourself, that's because 5 to the 10th power is congruent to 9 mod 23. All right, okay, so that was just the parameter generation. And now let's sign a message. So the message that we are going to sign is x equals 14. Okay, and really we generate the ephemeral key is generated for every message. So I guess I should have picked the message before the ephemeral key. But anyway, we pick this message, and then we pick the ephemeral key. It's ephemeral because it's used just once per message. And then we just follow the algorithm that we talked about a second ago. So first we compute R. So R is alpha to the KE. That is 5 to the 3 mod 23. And that turns out to be equal to 10. Okay, and now we figure out S. S is x minus dr to the KE inverse mod 22. So that is 14 minus 10 times 10 times 15, which turns out to be congruent to 8 mod 22. Okay, so in other words, R is 10 and S is 8. And the message is 14. So now it's time to transmit this. So we would transmit, you know, X and then our S. So in this example, it would be 14 and then 10 and then 8. So now let's do the verification step. So we need to compute b to the r and r to the s, beta to the r and r to the s. So beta to the r is 9 to the 10th because beta is 9 and r is 10. And this is congruent to 18 mod 23. And we compute r to the s, which is 10 to the 8, which is congruent to, whoops, 2 mod 23. And now we multiply these things together. So beta to the r times r to the s is congruent to 18 times 2, which is congruent to 13 mod 23. Okay. All right, so that's one side of the verification, and now we have to also compute alpha to the x. So alpha to the x is 5 to the 14th, which is congruent to 13 mod 23. Okay, and these two things are the same. So they agree, which is good, check. And so the signature is valid. All right, I know all of that is really complicated. I also implemented it in Sage over here, in case you're curious. That's just parameter generation. Okay, so here is this is for slightly bigger numbers. So now P is this big random number. Are you guys looking at the same thing that I'm looking at? I'm just going to do this just to make sure. So P is this big prime. Alpha is 11. That's a generator for the numbers mod P. star, and then beta turns out to be equal to this. So D is some random private key. The message is some random number. So now we do the signature generation. So you can't repeat the ephemeral key, and I'll show why in a second. It's because if you reuse the ephemeral key, the eavesdropper can recover the private key D, which is like the worst thing that could possibly happen if you reuse the ephemeral key. And there were some people back in the day when Bitcoin was like the software was not as good. I think people have like scoured the blockchain and found some examples of signatures that that reuse the ephemeral key, and they were able to steal those Bitcoins. And you can also tell when two signatures use the same ephemeral key, because R will be the same in both cases, because R is just alpha to the KE. So if KE gets reused, it sticks out, and so that's kind of a bad combination of facts. One, it's really easy to recognize two messages that use the same ephemeral key, and two, if it ever happens, you can recover the private key and then do whatever you want with it. So remember, the ephemeral key has to have an inverse mod p minus 1. That's what this while loop is for. So now we have KE and KE inverse. R is alpha to the KE mod p. And here's S. And it just turns out to be these two numbers. Now you can do the signature verification stage. So on the one hand, you do alpha to the X, and on the other hand, you do beta to the R times R to the S. And are they equal? And the answer is yes. And so signature accepted. All right, so I'm going to sketch now what happens if the ephemeral key is reused. I mean, the math is I don't know. All this stuff is if you read the book slowly, it's not so bad. But I assume that if you have not read the book and you just see me writing these things, it's very hard to understand. The important thing to remember 20 years from now is that if something is called an ephemeral anything in cryptography, don't reuse it. So suppose the ephemeral key is used twice. So suppose that the ephemeral key is used to sign both x1 and x2. Okay, so you get one signature S1, which is x1 minus dr times, oh, sorry, I guess I should say what R is, even though we said it verbally just a second ago. So R is always alpha to the KE mod P. So that'll be the same for the signature of x1 and for the signature of x2. So the S part of the signature for S1 will be x1 minus dr times KE inverse mod P minus 1. And S2 will be equal to x2 minus dr times the inverse of the ephemeral key mod P minus 1. So I'm gonna skip some of the algebra here. But now if you take the difference S1 and S2, then this KE factors out, and this part cancels, and what you get is x1 minus x2 times KE inverse mod P minus 1. So, these are all congruences. Okay. All right. Now you can solve this equation for KE. It's S1 minus S2 over x1 minus x2 mod P minus 1. So this is not literal division. This means multiply both sides by x1 minus x2 inverse. So that means x1 minus x2 actually has to have an inverse mod p minus 1, but there's a good chance that it does. And even if it doesn't, there are some bad things that could happen. So now when the ephemeral key is reused, now you know the ephemeral key, but how bad is that? It turns out that it's really bad because you can express D. So you just take one of these expressions like S1 here. Let me write that down again. So S1 is equal to X1 minus dr times KE inverse. So if I know that, then I can do KE S1. This will be, so this is all mod P minus 1, X1 minus dr. And so the target here now is to recover the actual private key, which you can with just a little bit more algebra. And so D is congruent to X1 minus S1 KE divided by R mod P minus 1. And now knowing D, you can sign whatever you want or spend as much cryptocurrency as you want. You know, ownership of cryptocurrency is equivalent to just knowing a certain private key. So if you know it, those are your coins. And I did this in Sage also. So here's the signature verification, but I did a little illustration of how to do the ephemeral key reuse to steal the key. So here are the public parameters. Here's the private key D. Now I have two messages, and I picked both of them at random, so nothing up my sleeve here. And here's the ephemeral key that we generate at random. And so now we sign X1 and produce a certain signature RS1. And now we sign X2 using the same ephemeral key. Notice that R really is the same in both these cases. That's R and that's R. You get different S's, but you can recognize that the signature is the same. I mean, that the ephemeral key is the same. So here is the algebraic formula that recovers the ephemeral key. And you can see that it works. Like here I'm deriving KE just from X1, X2, S1, S2. All that stuff's public information. So anybody can do this. So there's KE. And now that KE is known, everything on this side of the equation is also public information. It's just X1, S1, and KE is known. And R, and P minus 1. And so is it true that D is equal to that? And the answer is yes. So you have stolen the private key for El Gamal. Since we have a couple of minutes left, let me do one more thing. I know you guys must have El Gamal coming out of your ears. But there's a way to do an El Gamal existential forgery. And I will not go super into the details. It's kind of like the RSA existential forgery. Except that you have no idea how anybody was ever smart enough to actually think of this. But so just like before, Bob picks his private key, which is D, and he publishes his public key. So his public key is P, alpha, and beta. So everybody gets to see those things. So he puts them out on the wire. But then here is Mallory, who reads that stuff. And then what she does is she chooses I and J. These are integers. I can be anything, but it has to be true that the GCD of J and P minus 1 is equal to 1. So this is the first step. The second step is compute R. So R is alpha to the I times, notice this is not the usual formula for R. mod p. And she computes S, which this again is not the usual formula for S, minus R times J inverse mod P minus 1. And finally, so she got to, this is sort of like the existential forgery in RSA. You get to choose the signature. You get a free choice of I and J, which determine everything else. But once you choose the signature, the message is kind of pseudo-random. So this attack has that same problem. So S has to be equal to S times I mod P minus 1, which is going to look like a bunch of gibberish. But now anyway, if you were to compute using these values, so now X and RS go out, and if you were to try to verify that signature, then you would check the equation BR, R to the S, and ask if that is congruent to alpha to the X, which is alpha to the SI mod P. And just because these values were cleverly chosen, this would turn out to be true. And so the derivation is in the book, and it would be a good thing to go through if you want to. Okay, so the solution to preventing this is the same as in the case of RSA. You just need to use padding, or at the very least hash the message, and then this will be impossible. Okay, so what did we do? We explained the basic idea of digital signatures, and then we gave an example of a digital signature scheme that was based on the difficulty of integer factorization, which is RSA. And then we gave a different digital signature scheme, which is based on the idea of the discrete log problem, which is El Gamal. And then there's a further development of that DSA, the digital signature algorithm, which is sort of a development of an optimization of El Gamal. Both of these schemes have like huge keys, because they both involve a prime p. So p is at least 2,000, at least 1,000, probably more than 2,000 bits long. So these are fairly big keys. If you the discrete log problem can be done in any group, and so you can do it in an elliptic curve group too. And so there is an elliptic curve version of El Gamal and an elliptic curve version of DSA. And ECDSA is a very common signature scheme, and it's used in most cryptocurrencies. The reason is that when you use the elliptic curve, the size of the key comes way down to like 256 bits. And the reason that size is critical in things like cryptocurrencies is because these the signatures and the public parameters have to go on the blockchain, and it's very expensive to put a lot of data on a blockchain. So this is a cute way to do it. Like everything with elliptic curves, certain people are paranoid that the parameters chosen by NIST and the NSA for the elliptic curve part, this is a certain curve. I mean, you can't really visualize it like this, but it's an algebraic formula with certain coefficients. Those coefficients were chosen by the U.S. government, and so people suspect that they were chosen to give the NSA, for example, a backdoor into signature schemes or whatever. And there's never been any evidence that that's true. It's theoretically possible. So that's it. Does anybody have any questions? Maybe if you have a chance, you could go out and enjoy the beautiful day. Stay socially distant. Or sorry, physically distant. Have you guys heard people making that? They say, I'm not socially distant, I'm physically distant.
I've never heard that actually.
So, you know, I'll be around on Piazza and stuff if anybody wants to talk. I guess I could come by at 10 a.m. Tomorrow morning, like I've been doing recently. So I'll be there tomorrow too. And otherwise, I'm gonna go. I hope everybody has a nice day.
Same to you.
All
All right.
right. Bye.
Bye.
Okay. Bye bye, Professor.